Hi, we're going to talk about rotational dynamics. So let's get started. This is going to be mostly problem solving because the concept is pretty easy. We're just revisiting translational concepts in a rotational context. So we're going to look at kinematics, which you've already done, but in combination with Newton's second law. So we've got Newton's second law, right? Acceleration is proportional to net force and indirectly proportional to mass. And the rotational version of this is very, very similar. It says that angular acceleration is directly proportional to net torque and inversely proportional to rotational inertia. The angular acceleration and the net torque are always in the same direction. So you can only have angular acceleration if there's a net torque. That's all there is to it. If they're balanced, you're going to have equilibrium, which we've already examined. So we're going to really do some problems, and some of them will be pretty basic, and some of them are going to be more advanced. So I will walk you through how to do it. But the thing is that the problem-solving strategy is very similar. Notice you have to draw a careful sketch. You have to determine what you're looking at. Usually you're looking for an item that is rotating, and you're going to draw free body diagrams of any items that are moving. So you might have to draw a free body diagram of more than one object. Sometimes there's just the rotating object, and other times there's going to be things that are hanging on it, or that you also need free body diagrams for. It's also really important to identify the pivot point, and then you have to apply the rotational equivalent Newton's second law. I'm sorry about this typo. It just should say net torque equals alpha, sorry. So make sure you identify the direction that it's moving, and make sure you check the direction of rotation, that they agree to the direction of the net torque. So let's go over these problems. I'm going to do them with you, so I'm going to change my point of view so you can see my paper as I work things out. A rod is pivoted about one end. Two forces F1 and negative F2 are applied to it. Under what circumstances will the rod not rotate? So if here's the rod like this, right, and it's pivoted at one end, so there's the pivot, then if there's two forces, one up and one is negative, which I'm just going to make down, when will it not rotate? So it's not going to rotate when the net torque is 0. So how do you make the net torque 0? Well, torque caused by force 1 has to be equal to the torque caused by force 2. So they can either be in the same exact position, right? But you don't know that they're equal. All that you know is that the force 1 times its radius, right? It's R1, has to be equal and opposite to force 2 times its radius. So that's the circumstances. So it could be that force 2 is here, and here's R2. That would be fine also, but this product and this product have to be equal. So here's a problem. Consider the father pushing a playground merry-go-round. He exerts a force of 250 at the edge of a 200-kilogram merry-go-round, which has a 1.5 meter radius. Calculate the angular acceleration produced when no one is on the merry-go-round. So what is that going to look like, right? We're considering that as a disk. So before we start, we're going to draw a picture. So here's my merry-go-round. I'm going to draw a top view, and let's say the father is pushing this way. Just pick a direction, right? So they're showing him there. It just says his force is perpendicular to R. So here's my radius here, and we're given that this is 250. The mass of the platform is 200 kilograms. The radius is 1.5 meters, and we're looking for the angular acceleration. So you have to look up, it says that it's a disk, and the eye of a disk is 1/2 mr squared. You probably have to look that up. You don't know that off the top of your head, but just go do that and write that down as one of your givens. So the relationship that we're going to be examining is this one. And there's only one force acting on it. So torque, there's only one torque. So there's just the torque from this normal force is I omega. So since that's the normal force times its radius where it's applied, this is 1/2 mr squared, and alpha is what we're looking for. So this becomes not a very difficult problem. You have 250. One of these r's cancels with one of those, and you can do fill in the rest of the information, and you end up with 1.67 radians per second squared. Okay, oops, sorry about that. So that's that problem. So the next part of the problem is to calculate the angular acceleration produced when an 18 kilogram child sits 1.25 meters away from the center. So what changes here? Right, what's going to happen is you've got a kid sitting like right here, right? And here's his or her, we'll call it mass 2, right? So that child is putting a force at this point here. And it's a force that's not acting perpendicular to the direction of motion, so it doesn't add any more force. What it does is it changes the rotational inertia of the system. So it's not adding a force because the force has to be, you know, perpendicular. It would be acting in the plane, perpendicular to the plane of the disk's rotation, so it doesn't exert a force. So you're still going to have this net torque equals I omega, and the torque is still due to the normal force of the father, but now the I is due to the disk plus that of the child. So that's what changes. So you've got Fn times R of that normal force. This is still 1/2 m of the disk, r of the disk squared, and this is of the child. And for a point source, the it's not half, so the I of a point is just mr squared. So here we're going to put mr squared of the child, alpha. So now you can plug everything in. Now you can't cancel out the r's because they're not in it's not in every term. So you have to write the whole thing out. And the child's mass is 18 kilograms times 1.25 squared times alpha. So that's what it looks like. So you end up with 375 equals 225 plus 28 alpha, which is 1.48 radians per second squared. Now, this should make some logical sense because, right, if you add a person on, you're going to be able to accelerate less quickly. That's why this is lower, right? It's a very small child. 18 kilograms is like 35, 40 pounds, something like that. So you're talking about a toddler. It's really not going to make it very difficult for the parent to turn them. Okay, the next problem is this one. The fan blades on a jet engine have a moment of inertia of 30 kilograms per meter squared. In 10 seconds, they rotate counterclockwise from rest up to a rotation rate of 20 revolutions per second. So here's my fan. Beautiful, right? Here's my point of rotation. I've got the rotational inertia of the fan is given, so I don't have to calculate it. In the time of 10 seconds, we start from rest, and let's say this is 1, and then it comes up to 20 revolutions per second. I gotta convert that. 1 revolution is 2 pi radians, which is 125.7 radians per second. And they're asking me in part A what torque is needed to do that, and part B, yes, and part B is what's the torque to bring it to rest. Okay, to accelerate. So 2 parts. So the first thing that you need to do is you're going to write out your equation, and you need to find out what the angular acceleration is before you can start this. So given that you have these 3 things, you have initial and final and the time, you can do omega final equals omega initial plus alpha t. So this is 125.7 equals 0 plus alpha times 10, which means it's 12.57 radians per second squared. And then you have to solve for the net torque to accelerate it to that point. So the torque is going to be 30 times 12.57, which is 377 Newton meters. So that's going to be the torque required by the motor. So next part, if you have to slow it down in 20 seconds, so now you're going to do the same thing. Now this is 0, this is 125.7, and this is 20 seconds. So you're going to get probably 6, right? It's going to be a smaller value. 125.7 divided by 20 is going to be 6.29 radians per second squared. Right, and then it's going to bring it to, so now what's that going to be? It's 30 times that. So you need about half, you need half as much torque to bring it to rest. So that's the end of that problem. So what follows this are several problems on your own. So I would like you to give those a shot. You should pause this video and then you can start it up again in order to do the problems. So pause it at each problem and then you can see the answers afterwards. Come on the next slide. So don't move on until you've done each one.